Hello, everyone. My name is Stephen Shaughnessy, and I'm a lecturer from the Technological University in Dublin. And on behalf of my colleague, Frank Breitinger from the University of Lausanne and myself, I am presenting our paper entitled Malware Family Classification via Efficient Huffman Features. So to give you an idea of what this paper is about, Efficient Huffman Features, or EHF, is essentially an algorithm based on compression. The idea was to produce a machine learning ready feature set without the need for any kind of manually intensive pre-processing, feature extraction and feature generation steps. So to give you some background issues that I suppose motivated this study, well, malware is constantly on the rise. It's hardly breaking news, but what is interesting is that malware, the new malware that we're seeing, is generally kind of staying stable, whereas the variants of these original strains are constantly rising at an almost exponential rate. The classification of these variants is important in order to kind of group them into their correct kind of, I suppose, taxonomic class based on similar traits and behaviors. The problem with that is malware is essentially a binary file. So these traits and behaviors that we can extract are not readily available. So we need to have, we normally need to use some sort of pre-processing stage or pre-analysis stage to extract features. Generally, these feature extraction approaches are quite labor intensive. They can be invasive. So for example, using reverse engineering or disassembly. And so may not scale well to large data sets. Additionally, then, they require knowledge of the malware's internal binary structure, because we need to know the internal binary structure in order to know where that interesting information is. On top of that, then, feature selection, which is the, once we've gathered or extracted the features, we also need to be able to select the correct features for classification. Because if we select incorrect features, then the classifier will, learn incorrect traits that will throw off its predictive capabilities. The problem is, by and large, malware analysts are not data scientists, and so the choosing or the selection of the correct feature sets can be quite challenging. So the motivation for this was to produce almost an automated solution whereby we didn't have to have any feature extraction or feature selection processes before we actually got the data into a state that we could use it for machine learning classification. So I first looked into compression. So if you're thinking of the likes of 7-zip or WinZip or BZip, you'd be correct. So in terms of what a compression algorithm does, well, essentially it encodes data into a reduced representation of fewer bits, usually for reduced storage or for reduced bandwidth if it's been transmitted over a wire. For our purposes, we can think of compression as representing our data or our files with less data, so essentially a subset of the original data. The advantage of compression as well is that can be employed to data in any format. So this has the potential to be used in a wide variety of domains. So it's not just limited to malware classification. In terms of what's been done before and for compression, mainly the works have concentrated on distance metrics. So the main one being normalized compression distance, or NCD. This has been shown to be used in a wide variety of domains, like text classification, genomics, virology, even music classification. So it's found to be an effective metric. The LZJD and Schwell algorithms were based on the Lembel-Ziv algorithm, compression algorithm, and also were shown to be effective particularly in the malware classification space. In terms of compression as a feature space, there has been work done to show that the dictionaries produced by some of the algorithms, such as the invasive variants, can be engineered as feature vectors. And that was the case with the likes of LZJD and Schwell. The authors did use, they used min hashing and feature hashing in order to convert or engineer those substrings into features that could be used for classification. We've seen the LZ algorithm being used for text classification problems as well. Some of the limitations with these approaches, though, in particular, NCD is computationally inefficient. So to calculate the similarity between two input sequences, we need to calculate 3 compression processes. So we need to compress not only the input strings or input sequences A and B, but also the concatenation of A and B as well. So essentially, you have 3 compression operations per similarity metric measurement. And so this becomes infeasible for large data sets. The LZ variants have been shown to produce very large feature spaces. So for example, the LZ variant LZ77 produces an exponential feature space. So as our data inputs grow, so the number of our files that we're processing grows, so too does the feature space to represent those. And again, the likes of the LZJD and Schwell algorithms, the authors have had to use feature dimension reduction in order to make this kind of feasible as a kind of a feature space. I kind of highlight the LZJD and Schwell algorithm because although they are essentially a distance type metric, they do produce a set, a feature set based on the LZ algorithm that is essentially a feature vector. And so in some ways then are similar to the EHF algorithm that we produced. So based on the findings there, I wanted to find an algorithm that was efficient and produced a small feature space. So I settled on Huffman coding, essentially just because of the way the algorithm works. So it's based on the frequencies of occurrences of the input symbols, which are essentially the characters within the input sequences. So the input sequence in our case is a malware binary. So if you think of it, we're representing, say the extended ASCII set. So the maximum amount of characters or symbols within our alphabet is 256. So that equates to essentially the maximum feature size or feature dimension size of our vector is going to be 256, which is markedly smaller than the likes of the LZ algorithms. So just to give an idea of how Huffman works, essentially what it does, it generates a binary tree based on the frequencies of occurrence of the characters, such that the tree produced the lower nodes on the tree, or the end nodes on the tree, will be the input symbols with the lowest frequency, so the lowest frequency of occurrence, whereas at the top of the tree, the symbols with the highest frequencies will tend to be. So to give an example of how it actually works, of a simple string there of 22 symbols, 22 characters, A, B, and C. So we first of all start off by calculating the frequencies of each. So we've got 4 A's, 6 C's, and 12 B's. The iteration of the algorithm works by removing the first 2 lowest frequencies from the set and adding it to a subtree, or creating a subtree. The parent node being the summation of the weights of, or the frequencies of, the 2 child nodes. So for instance, our example, A is 4 and C is 6. So the parent node is going to be 10. And that's added back then into the set. And then that process is repeated until we get a full binary tree. And we essentially only have 1 node left in our set. The actual Huffman code word, which is essentially the representation for the the symbol or the character is obtained by following the edges from the root down to where the node is on the tree. And using I should have said that as the tree is constructed, the convention is that we add a 0 to the left-hand child and a 1 to the right-hand child, and these are used then as the binary code word as we construct it. So if you look at our example, the Huffman code word is obtained by following the root node down to A, so that's 0, 0. C is 0, 1, and B is 1. So instead of representing, say, for example, each symbol in terms of 8 bits, which would be 22 by 8, which would be 176 bits, we can now represent A with 2 bits, C with 2 bits, and B with 1 bit, which works out 4 by 2, 6 by 2, plus 12 by 1, which is 32 bits. So that's essentially how the Huffman coding algorithm works. The EHF algorithm is a kind of I suppose, an extension of that. So it calculates the code words in the same way as before. But what it does at the end then is it combines the symbol, which is converted to its decimal equivalent, the integer value of the code word, the binary code word, and then also the frequency itself. So initially I just used the Huffman code word as the feature for classification, but I found that the models that were produced didn't generalize well, so they weren't robust against kind of unseen samples. And so I kind of went back to the drawing board and I said, well, you know, if you look at what we're producing here, the symbol itself can be represented as a number, which is important, obviously, because we're dealing with, you know, individual unique symbols. Its frequency, so if a malware sample is almost the same, two variants are almost the same, then they will share the same symbols. They will share more or less the same frequency of symbols as well, and the code words will be quite similar as well. So I combined those 3 values into a composite feature and use that then to represent each symbol. So essentially the output from the EHF algorithm is a vector. So the dimensions of the vector depends on the input of the characters or the symbols within the data. So like I said, the maximum size or the maximum dimension is 256. I suppose just to note that because we're dealing with variants of binary files, there may be some alphabetic symbols missing or not present in certain files. And so the EHF algorithm may produce variable length vectors. So for classification, we need to have a uniform sized vector. So the dimensions need to be the same for classification. And so to kind of get around this, I resized all of the vectors to the k kind of smallest dimension vector. So for example, the smallest dimension vector in the data set that I used for the experiments was 229. So I reduced all of the other vectors in the set to 229 dimensions. So the way that the Huffman algorithm works, it's sorted based on code words. So the least kind of frequent code words or the least frequent symbols will be towards the end of the set. So any features that I've trimmed off will tend to be the lesser frequent symbols within the input sequence. So we'll have kind of a less of an impact on the actual overall kind of classification of the malware. So the data that we used was primarily the Win32 portable executable files, so P files, which are essentially, the kind of the most common type of format that we can find malware in. These were extracted from several repositories on the First Total academic share from around 2018 up to 2021. I used an open source tool called AV Class Labeler, which enabled me to cluster the malware together based on family class. So it uses the output from the First Total AV scanners to label the malwares according to their family. Initially, I used a training set of around 8,000 samples from 12 families. The reason why I've extended that then for further testing is because we just decided that we needed just to test how well the models generalized onto kind of different and more families. So I extended it up to around 14,500 from 23 families for kind of the latter stages of the testing. And in terms of the classification, then once we had the data into the feature sets, the data and the labels were split in a 90-10. So 90 being the training and testing, and 10% then was held back then for evaluation, for evaluating the models on unseen data. I primarily chose k-nearest neighbor as the algorithm because it's a distance-based metric, and some of the experiments that I was conducting were based on NCD. So I wanted to be able to interchange the distance metrics easy enough, which I could do with k-nearest neighbor in order to kind of evaluate it against the NCD algorithm. So I use parameter tuning to find the best or optimum parameters for the KNN classifier, and I also use five-fold cross-validation in order to kind of reduce kind of overfitting and classification errors. The metrics used are precision recall and accuracy. Just because accuracy alone, I don't think, which was found in most cases in previous works, doesn't give a kind of a good overall picture. So precision recall will obviously give a better indicator of how the models performed. So the results on the initial training set were good. 11 out of the 12 families were predicted with a TPR rate of 97% or above. One family in particular performed kind of markedly poorer, which was the SCAR family. I did some further digging on that, and the two classes that it was kind of misclassified as, being Autowit and Vilcell. When I checked out, I ran them through the VirusTotal API, and it was found that in many cases there was kind of mislabeling, or you know, SCAR would be mislabeled as Autowit, say, for instance, in some cases. So that could be, you know, the reason why for that mislabeling. Once the models were created, the 10% evaluation set returned pretty good results as well, in around 97% for the three classification metrics that were used. Excuse me. I wanted to run a comparison with NCD, even though NCD is primarily a distance metric. I wanted to show that EHF could be used in conjunction with a standard distance metric in order to, you know, produce a kind of an efficient way of similarity comparisons. And so the table there shows the runtime for the comparisons for each data point, or each kind of feature essentially in the feature set. So you can see that the Minkowski EHF algorithm ran at roughly around 1 millisecond per comparison, as opposed to 1.2 seconds with NCD, which is pretty much 3 orders of magnitude slower. Likewise, the Minkowski EHF algorithm outperformed NCD by roughly around 20% as well. So that just proved that, you know, EHF, along with some standard distance metric, is a viable method for kind of similarity measurements for malware. I compared and evaluated EHF against LZJD simply because, again, I suppose the LZ sets that were produced from both algorithms were essentially feature sets that could be used for classification. And I wanted to show kind of a similar kind of method, and again, evaluate how well EHF would compare to those. So in terms of feature generation times, EHF had an average of around 50 milliseconds, as opposed to 120 with LZJD. And LZJD Schwell algorithm was around 500 milliseconds, which is obviously 10 times slower than EHF. In terms of training time, then again, EHF was roughly around 3 times faster than the LZJD Schwell algorithm, and roughly probably around 7 times faster than the LZJD. A lot of that is obviously down to the feature dimension size as well, because the feature dimension size for both LZJD variants is 1024, as opposed to EHF, which had a feature dimension size of 229. The second comparison then with LZJD was for classification performance. So this was on the larger virus total data set of the 15,500 samples. So the Schwell algorithm performed slightly better than EHF, roughly around 0.1 to 0.4% over the three metrics: precision, recall, and accuracy. But in terms of the validation on the 10% data set, EHF outperformed both LZJD variants quite considerably. Now, just to put in a note there that I didn't do any kind of, I suppose, parameter tuning or dimension reduction or anything like that in terms of the LZJD. So if we did spend a bit more time on that, the results might have been different in terms of performance for the LZJD. But again, this was used to evaluate the EHF as a kind of a viable method, I suppose, of classification for malware. The last set of tests I did was on code reordering. So I used an import table. The import table is extracted from the virus total data set. They were trained on the classifier as before. And then I used a tool to basically reorder the code, and as such reorder the import tables. The import tables were extracted from the subsample then, and then were run against the KNN model, which produced an accuracy of roughly around 100%, very, very high recall, precision, and accuracy. The reason why I conducted this experiment and this set of tests was just to show that the way EHF works and the way Huffman works is because it works on the frequency of occurrence of symbols, the order in which the data is input doesn't matter. So if two files are the same, if they're reordered in any way, then the sets produced from the EHF algorithm should be the same, because the alphabetic symbols will be the same, the frequencies will be the same, and so on. And so, that was this test was essentially to kind of show that. In terms of feature optimization, I played around with the number of features just to see its effect on classification error. So for the example I have here, I reduced the dimensions of the VT set down from 229 to 250, which is approximately from 105 to around 85, which is approximately 20% of a less compute time, which you can see on the right-hand side. And then if you look at the corresponding error rate, it increased only by 0.4. So the significance of this is if we want to run this at scale and we have a large scale data set, then we may want to optimize the algorithm by lowering the features. And, if we can afford a slight trade-off of an increase of an error, classification error, then, we can greatly optimize the algorithm at scale. Again, this is dependent on the data, so I don't have any information on other data sets, but for this particular data set, roughly, dropping the features down to 150 only had an increase of 0.4. So just to give a summary of the contributions of this paper, we've produced an algorithm called EHF, which is based on compression, which negates the need for any kind of invasive pre-processing, and gives a set of features that are ready for machine learning. It's quite fast. It's built on Python. It can be improved, but at the moment it's built on a heap structure, which is quite fast, and so is scalable to large data sets. It's free and open source. So in the paper, I do provide a link to the repository. It has the potential to deploy to other domains because it's based on compression. We can compress pretty much any file. So it has the potential there to be used to be used in other domains, not just malware classification. And the outputs then are in such a way, in such a format, essentially that they're ready to be plugged into machine learning algorithms. They're essentially a feature set that represent the malware binaries, and that we can just pass to any machine learning algorithm then. Some of the limitations, EHF is I suppose, in its infancy. I only developed it in January, and as such, we developed the tests, and subsequently, I suppose, wrote the tests around the paper because when I spoke to Frank about this in January, we decided that we wanted to put it into this conference, and obviously we had a short deadline. And so we designed the experiments to fit into the paper in the short space time that we had. There obviously are limitations there that we can address. We limited the malware experiments to executables and import table dumps. But like I said, we could probably implement this in any type of data type or data format. I only use the KNN classifier. Again, I use it out of convenience because it's a distance-based classifier, and I could easily interchange the distance metrics to have a comparison or evaluation against the NCD algorithm. And then obviously, there is lots of other obfuscation methods such as packing and encryption that weren't tested. Again, this is down to time, and obviously that's something that we could explore further. So, in terms of future work to test at scale, at the moment I've unsuccessfully tried to download Sorel data set, which is it's 8 terabytes. I've managed to download 2.5 terabytes before, the connection seemed to just crap out. I don't know why. So hopefully over the summer I'll get to download the whole data set and work on that. We'd like to improve the processing speeds, obviously, because if we're looking at large scale processing, we need to have something faster. So we could use maybe a different language, or use maybe C bindings in Python to do that. Could be applied to other forensic scenarios. So one that comes to mind will be, say, file fragment identification. And again, because we're dealing with compression, that is a possibility. And then obviously the further obfuscation testing to test on the likes of packing or encryption and see if EHF can pick up, any of those kind of obfuscated samples that are within a data set. Okay, so that concludes my talk. I just want to thank the organizers for the Digital Forensic Research Workshop for allowing us to present today, and I'll answer any questions that you may have now. Thank you.